In this video, we're going to discuss topics from 5.5, which are bases other than E and applications of working with bases other than E. Before we get into that, though, let's talk about e to the x, and then I'm also going to want to refresh you on hyperbolic sine and hyperbolic cosine, which are related to e to the x, and we didn't really discuss those in depth in the Calculus 1 topics. I just discussed it very briefly at the end of the last video, and I think it fits better right here. So let's go ahead and recall. Well, let's look our objectives here to define exponential functions that have bases other than e, and to differentiate and integrate exponential functions that have bases other than e. So recall from the properties of the natural exponential function, that would be y equals e to the x is what we're looking at. That the domain of f of x equals e to the x, or y equals e to the x, is negative infinity to infinity for the domain, and that the range is going to have a horizontal asymptote here at y equals 0. So it's going to be bounded below by y equals 0, and 0 is not included. It approaches but never gets there, so that's open on that side. To positive infinity, it goes up forever. The function f of x equals e to the x is continuous everywhere, it's increasing everywhere, and it's one-to-one everywhere in its entire domain. The graph of f of x equals e to the x is also concave up on its entire domain. So this would also be positive everywhere if that matters to you. That's more of a pre-calculus thing, but this graph is always going to be greater than 0 because of its range. So it's positive, it's increasing, so its first derivative is positive, and its second derivative is positive everywhere. Interesting function like that, right? Now, its right-hand behavior and its left-hand behavior are different. So as I go to the left, it has this asymptotic behavior here. The limit as x approaches negative infinity of e to the x is going to be 0. As I go to the right, its right-hand behavior limit as x approaches infinity of e to the x is equal to infinity. It goes up to infinity over here. So those are important things to know about e to the x. And all exponential functions are going to resemble this. They're just going to have been stretched. If you remember that you have the general form of f of x equals a times f of x minus h plus k, where you have this a stretched things vertically, and this h shifted things horizontally, and this k shifted things vertically. Well, a in our problem here, it seems strange that it's going in as the base and not a constant multiplier out front, but a is going to be responsible for this vertical stretch or shrink. This point here at 0, 1 is going to stay fixed no matter what the base is, but this point is going to shift to be 1a, and then negative 1, 1 over a, and so you're going to get a stretch like this. Or if a is between 0 and 1, you're going to get 1 right over here. You're going to get 1a, and then 1, negative 1, 1 over a will actually be up here. And it'll come this way. I know that looks kind of strange to have it change direction like that, and then some of these things would change which side the asymptote is on, whatever, but we're going to have different properties coming up here for if a is greater than 1 or if a is between 0 and 1. We don't want it to be 0, we don't want it to be 1. But it's okay for a to be between 0 and 1, or for a to be greater than 1. That's kind of all pre-calculus stuff. Hopefully you remember that. Let's finish up talking about the calculus stuff here before I jump in and talk about hyperbolic sine and hyperbolic cosine. The derivative of e to the x is e to the x. So if we want to make that the general form using the chain rule, the derivative of e to the u is going to be e to the u times du dx. For integration, the integral of e to the x dx is e to the x plus c. I think you see why we like this function mathematically, because it just keeps coming back as itself. The integral of e to the u du is going to be e to the u plus c. So the natural logarithm function is also the inverse of the natural exponential function, meaning right here that if f of x is equal to e to the x, the f inverse of x is ln of x. And I can compose those two functions either way and get x by the definition of an inverse function. So if I take e to the ln of x, those properties will tell me that that's equal to x, as well as ln of e to the x will also equal x. All right, so two special exponential functions that we need to know about, especially before we go into differential equations. It's going to be hyperbolic sine, which is equal to e to the x minus e to the negative x over 2, and hyperbolic cosine, which is equal to e to the x plus e to the negative x over 2. I'm going to leave it to you to prove to yourself that the derivative with respect to x of sinh, so the way I say that, hyperbolic sine is going to be cosh, and the derivative with respect to x of cosh is going to be sinh, and that means that the integral with respect to x of sinh is going to be cosh x plus c, and the integral with respect to x of cosh x dx is equal to sinh x plus c. So they just swap places back and forth because of this e to the negative x. When I take the derivative here, I'm going to be multiplying by -1 and getting that to turn positive. The e to the x stays the same. The 1/2 constant multiplier just stays there. So it's just this, whether I differentiate or integrate, that's switching signs back and forth so that sinh becomes cosh and cosh becomes sinh. Don't worry too much about what hyperbolic functions are. It's kind of like trigonometry based off of a hyperbola instead of based off of a circle. That's what it means, where sine and cosine are based off of the circle. This is different. So we'll get into some conics and things later, and you might see how this is beneficial when we're dealing with certain shapes. But you do not need to know all of the trig identities for hyperbolic trig functions right now. There's a couple of them that would be beneficial to you. You can look those up in the textbook in chapter 5 if you would like to know them. We're not doing a whole section of notes on that, but I wanted to throw that in here. All right, let's move on to exponential functions of base A. And I already talked about how that A is related to the A that is the stretch shrink factor. So if A is a positive number with A not equal to 1, and obviously we don't want it to be equal to 0 either, and x is any real number, then the exponential function to a base of A is denoted by A to the x and is defined by f of x or y equals a to the x, and we can rewrite that a as e to the ln of a, since we know a is going to be equal to e to the ln of a. The log, the ln and the e will undo each other and leave me with the a. So I can write it this way, and then I can think about using the chain rule to get my rules here. So remember that if I have multiplication of exponents here, that came from raising a power to a power like that. So if I have right now a to the x and I want e to the ln of a is going to be my a raised to the x, then I'm going to multiply these two exponents together here and get e to the ln of a times x. And that's how this expression on the right comes, is by raising a power to a power and multiply the exponents. All right, so exponential functions are used to model interest rates, radioactive decay, population growth, disease spread, anything where the rate of change is proportional to the amount present. It's more a differential equations idea, but I'll get you thinking of it right now. So anything that as you have more stuff, that the rate of change is going to happen faster if you have more stuff than if you have less stuff. You're going to have a smaller rate of change. So that's what happens with compounding interest, that if I have more money in my bank account, then my rate of change of how much money I'm going to earn in interest is going to increase, simply because the principal has, or the amount of money in the account has increased. As that grows, I earn interest on the interest and so on, and it compounds. That's the idea of that. Radioactive decay. The decay happens proportionally to the amount of radioactive isotope that's present. As I get less of the radioactive isotope, the decay happens slower. Population growth, as I have more people to have more children and they have kids and so on, or it doesn't even need to be people. This can be bacteria colonies, or this can be a herd and things like that. Also epidemiology with the spread of a disease. We even see this in how quickly something cools, like when we take a cake out of an oven or something like that. And we may even see this in other things as well. So just leave that there for right now, that there's lots and lots and lots of real life models that are going to come back to exponential growth and decay models here. So the logarithmic function to base a, if a is a positive real number with a not equal to 1, and x is any positive real number, then the logarithmic function to the base of a is denoted by log base a of x, and is defined as log base a of x is equal to 1 over ln of a times ln of x. So this is another way to write this, is ln of x over ln of a. And you probably learned this as your change of base formula in pre-calculus. And we're going to be able to use that change of base formula here to write this 1 over ln of a as a constant multiplier. Here, and then we'll be able to figure out some of our derivatives and integrals and things like that from there. So don't forget your important log properties from pre-calc. log base anything of 1 is 0. Log base A of a product here is going to be the sum of the logs of that same base from the factors of the product on the inside. So log base A of X plus log base A of Y. If I have a power function inside of a log base A of X to the N can come down front. We already did that in some problems that we worked with natural logs last time. So the N comes down front using our log properties, N log base A of X. And if I have the quotient rule here for logs, log base A of X divided by Y, that's going to be the difference here of the of the ratio here. And the part that's in the denominator is the part that has the negative, because remember, things in the denominator, if we bring them across the fraction bar, they'd have negative exponents. So the things in the top stay positive, the things in the bottom are subtracted. So this is log base A of X minus log base A of Y. So if I had something like log base A of X, Y over Z, we would have log base A of X plus log base A of Y. They stay positive because they're both in the top. Then I would subtract off log base A of Z because it's in the bottom. If I had log base A of X over Y Z like that, that would be log base A of X minus log base A of Y, since the Y is in the bottom, minus log base A of Z. So hopefully you picked that up in pre-calculus when you expanded your logarithms. If not, now you have a simpler way to not need to do quite as many steps for your expansion using your log properties there. Let's go ahead and let's look at some examples here and just solve some exponential and logarithmic equations. So remember, the x to the negative a is equal to 1 over x to the a. For this problem, that's one of our exponent rules. So if I want to think of 1 over 81, that's 1 over 3 to what power gives me 81? Well, that's 1 over 3 to the 4th power. That if I take 81, that's 9 times 9, and this is 3 times 3, and another 3 times 3, so this is 3 to the 4th using factor trees. So 3 to the x is going to be equal to 3 to the negative 4th using this property right here. We're going to rewrite from right-hand side to left-hand side, and then using our one-to-one property from exponential functions from pre-calculus. If the bases are the same and the functions are equal, then the exponents have to be equal, because for me to have the same output, I have to have the same input with a one-to-one function, and all logarithmic and exponential functions are one-to-one functions. Now, are there other ways I could do that to use my calculator? Sure. I could take the log base 3 of both sides here and say x is equal to log base 3 of 1 over 81. And you may be able to put that into your calculator just like that if you have a fancy calculator. If you don't have a fancy calculator, then you may need to use your change of base formula and say that this is ln of 1 over 81 divided by ln of 3. And if you do that, you'll get your answer of -4. Even simple $20 scientific calculators will be able to have an ln or an log button here. You can use common log as well. It will also work. But we just like natural log in calculus because of the way in which natural log is related to e to the x, and e to the x is just such a fun function. All right, so we're going to now talk about how we can use our log properties to help us rewrite this logarithmic equation into an exponential equation. Let's remember our triangle of power that I've told you about, that 2 to the 3rd is equal to 8. And that can also be written as the cube root of 8 is equal to 2. And it also can be written as log base 2 of 8 is equal to 3. See how the logarithm, the log is equal to the exponent here. When written in exponential form, that's going to be important. So if I can write this as a logarithmic equation, log base a of something is equal to my answer, I can rewrite it here, knowing that base, the exponent is equal to n, if and only if log base b of n is equal to e. But those say the same thing to me. I also have a way to write it with roots. That's just not our focus right now. So using my log properties, I see addition of logs with the same base. So I'm going to rewrite that with multiplication on the inside. This is x squared minus 2x. Before I get any further, though, I don't want to just combine logs together and maybe start rewriting this and change the domain. So let's go back to my original here and look at my domain. The x has to be greater than 2 because both x and x minus 2 have to be greater than 0 by the rules for logs. So which one forces both of them to be true? Well, there are some numbers that are greater than 0 that are not greater than 2. So x greater than 2 is stronger, that if I pick something greater than 2, it'll also be greater than 0. That's my domain that I want to use to force both pieces here to exist so I can add them together. So I'm going to ignore any answers that I get for x being less than or equal to 2. They won't be in my solution set. Now I'm going to rewrite using this Ben formula here. So x squared minus 2x is going to be equal to 3 to the first, which is 3. So x squared minus 2x minus 3 is going to be equal to 0. I'm going to factor. It's going to be x plus and x minus and what? Minus 3 and plus 1. So that negative 3 plus 1 is a negative 2. Gives me x plus 1 is equal to 0, or x minus 3 is equal to 0. X is equal to negative 1, or x is equal to a positive 3. Now we just said that we don't want any answers that are less than or equal to 2. So negative 1 is less than or equal to 2. It's not in the domain of the original. So it's what we call an extraneous solution. And you see the word extra in there. It's an extra solution because we changed the domain of the problem that we need to ignore. So our only answer here is x equals 3. Sometimes you may get more than one answer to this type of a problem. Sometimes you may get no answer to this type of a problem. So you need to check your domain closely, go back to your original to check your answers. If I tried to stick negative 1 into the original problem here, I can't take log base 3 of negative 1. That's not a real number, nor is log base 3 of negative 3. But if I take log base 3 of 3 plus log base 3 of 3 minus 2 is 1, is that equal to 1? Well, that's 0 because log base anything of 1 is 0, and log base anything of itself is definitely 1. So 1 is equal to 1. All right, let's look at our rules here for differentiation for bases other than e. Because of how I can rewrite this using the chain rule, I'm going to have, this was in the form of e to the ln of a times x is y. So y prime is going to be the derivative of this exponent is ln of a times e to the ln of a x. So y prime is going to be ln of a, and then all this was the same thing as a to the x. So that's where this rule comes from. And if I want to just change that using u substitution, my x's become u's, but I need to multiply by du dx on the end. Now, if I have my change of base formula rule, that log base a of x, that's going to be equal to ln of a, ln of x here. So 1 over ln of a just stays there, and this ln of x becomes 1 over x. Remember here that x has to be greater than 0 already for this log right here, and same thing right here. So it might not be a bad idea for you to remember that this needs to be positive down here. That's not part of our formula, but remember that your domain is restricted to only positive values for x or for u here. All right, let's go ahead and evaluate the derivative with respect to x of 2 to the 4x. So we're in this situation right here where we have an a to the u. So a is equal to 2, u is equal to 4x, du dx is equal to 4. So let's plug and chug. This is going to be ln of 2 times 2 to the 4x times 4 is going to be 4 ln of 2 times 2 to the 4x. Now we want to find the derivative of y equals log base 6 of sine of x. So a equals 6 here, u equals sine of x, du dx is going to be cosine of x. So we want 1 over ln of a times u, which is sine of x, times cosine of x, which is our du dx. So that's going to be cosine over sine is going to be cotangent of x over ln of 6, like that. And your ln of 6 might be broken up, like ln of 2 plus ln of 3, maybe not. I don't know. But these are exact answers here. Now that we know how to differentiate y equals a to the x, we can also integrate. And we can get a to the x dx is equal to 1 over ln of a times a to the x. Just differentiate the right-hand side to prove that to yourself, that we have 1 over ln of a just sits there. We have a to the x times ln of a for our differentiation rule, and the ln of a's will cancel and give me a to the x plus 0 is a to the x. Sure enough, that's my original function right there. So this 1 over ln of a has to be there to undo this ln of a multiplier right there. So that makes sense. Don't forget that if you have the chain rule, there needs to be a du on the end. So in this case, my a is 2, my u is a negative x, So my du is a negative dx. I need to have a negative dx here. That gives me a negative out there. This is going to be a negative 1 over ln of a, like that, and then a to the x, like that, or a to the u, time, and plus c. It's a terrible looking ln. There we go. And a little more complicated here. A equals 5, u equals a negative x squared, du is going to be a negative 2x dx. So we need a negative 2 multiplier on the inside and a negative 1/2 multiplier on the outside. That's going to give me a negative 1/2 times, and then ln of 5 will be down here. 5 to the negative x squared will be up there. Then plus c. So that all comes together as a negative 5 negative x squared over 2 ln of 5 in the denominator plus c, like that. That's going to be it for this video. We'll come back next time and talk about 5.6 with some indeterminate forms and L'Hopital's rule. See you for the next video.